Hi there, Miss Barber here. The title of this lesson is Geometric Sequences. The learning objectives for this lesson are 1. Be able to recognize and identify parts of a geometric sequence. 2. Be able to compute partial sums of a geometric sequence. 3. Be able to compute the sum of an infinite series if it exists. Roman numeral 1, Geometric Sequences. A geometric sequence is a sequence of the form a sub 1, comma, a sub 1 times r, comma, a sub 1 times r squared, comma, a sub 1 times r cubed, comma, dot, dot, dot. The number a, or a sub 1, is the first term, and r is the common ratio of the sequence. The nth term of a geometric sequence is given by the formula a sub n equals a times r to the power of the quantity n minus 1. Find the first 5 terms of the geometric sequence defined by a sub n equals 3 times 2 to the power of n minus 1. So we'll find a sub 1, that's the first term. We'll have 3 times 2 to the power of 1 minus 1, which would be 3 times 2 to the power of 0, which is 3 times 1, or 3. Let's find the second term. It'll be 3 times 2 to the power of 2 minus 1, which is 3 times 2 to the power of 1, which would be 3 times 2, that is 6. A sub 3. 3 times 2 to the power of 3 minus 1, 3 times 2 squared. 3 times 2 squared is 4, and 3 times 4 is 12. You should be seeing a pattern about now. A sub 4 is equal to 3 times 2 to the power of 4 minus 1, which would be 3 times 2 to the power of 3. That's 3 times 2 to the 2 cubed is 8, and 3 times 8 is 24. Notice that the terms are doubling. Let's go ahead and find the fifth term. A sub 5 is equal to 3 times 2 to the power of 5 minus 1, which is 3 times 2 to the power of 4, which is 3 times 2 to the 4th is 16, and 3 times 16 is 48. Find the formula for the following sequences and the 15th term. 3, negative 9, 27, negative 81. We observe a common ratio, that is, the gaps between each successive term changes by a factor of negative 3. Now the formula for the nth term of the geometric sequence is a sub n equals the first term, and sometimes we write the subscript 1, sometimes we don't. Be flexible on that, times r to the power of n minus 1. Let's put in the information we have. A sub n is equal to the first term of this sequence is 3. The ratio is negative 3, and we raise this to the power of n minus 1. That's the nth term, or the formula, and to find the 15th term, we evaluate the formula at n equals 15, so it'll be 3 times negative 3 to the 15 minus 1, and let's just write this as 3 times negative 3 to the 14th. You can do a little bit more simplifying, but this is good for us. Let's do part B. 1, comma 1/5, comma 1 over 25, comma 1 over 125, comma 1 over 625. I see a pattern here. The common ratio here is a factor of 1/5. The formula that we use to get the nth term of a geometric sequence is a sub n equals a sub 1, that's the first term, times the common ratio raised to the power of n minus 1. So we'll write a sub n equals, the first term is just 1. The common ratio is 1/5 to the n minus 1. We can clean this up 1 doesn't change anything, so we'll write this as 1/5 to the n minus 1. Now, if we need to get, and it's also good to put the 1/5 in parentheses, now we need to get the 15th term, so we evaluate this geometric sequence at n equals 15, so we'll have 1/5 to the 15 minus 1, which would be 1/5 to the 14th, and we'll clean this up and write it as 1/5 to the 14th. The 4th term is 12, and the 7th term is 32/9. Find the first and the nth terms. This is on the assumption that this is referencing a geometric sequence. So when we work with geometric sequence, we recall that the nth term, a sub n, is equal to the first term times r, the common ratio to the power of n minus 1. Now, if we're told that the 4th term is 12, then we know that a sub 4 equals 12. Let's put that information into the general term, so we can write 12 is equal to a times r to the power of 4 minus 1, or 12 is equal to a times r cubed. Let's do that also for the 7th term. That is a subscript 7 is equal to 32/9. Put that in the nth term for the geometric sequence. And so this will be equal to 32/9 is equal to a times r, and this is going to be raised to the 7 minus 1. So what little bit we can do is clean this up. So we got 32/9 is equal to a times r to the 6th. Now we have a system of 2 equations and 2 unknowns, and that's enough information for us to be able to solve. So let's look at that. We've got 12 equals a times r cubed, and 32/9 equals a times r to the 6th. Let's just write the ratios of them. So I'll write a times r to the 6th equals 32/9, and a times r, what was the other one? Cubed, equals, and that number is 12. Now some nice things happen. The r's cancel, and we can use the rules of exponents and simplify the left-hand side to r cubed. On the right-hand side, we have some arithmetic to do. That is, we're going to have 32/9, and if you divide by 12, it's multiplying by 1/12, and this will give us, multiplying across, 32 divided by 108, get common factors, and 32 over 108 reduces to 8/27. How nice is that? The cube root of 8 is 2. Cube root of 27 is 3. So far, we haven't answered any of the questions. We haven't got the first term, and we haven't got the nth term, but we have enough information now to actually solve for the first term. So let's use equation we got earlier. 12 equals a times, and then r cubed, which we just solved for, is 8/27. Let's solve for a. A is going to be 12 times 27/8. Multiply across, I get 324 divided by 8. Reduce some of the terms, and I get 81/2. Now we can write the nth term. So note, we got a, that was the first term, and for the nth term, we need to fit the formula, so we're going to have 81/2 times, the common ratio is 2/3 to the power of n minus 1. Roman numeral 2. Partial sums of a geometric sequence. For the geometric sequence, a sub n, equals a times r to the power of the quantity n minus 1. The nth partial sum, S sub n, equals, the sum as k goes from 1 to n of a sub k equals a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus dot 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 plus a sub 1 times r to the n minus 1 for r not equal to 1 is given by the formula S sub n equals a sub 1 times, the numerator is 1 minus r to the n, all divided by the denominator of 1 minus r. Find the partial sum of the summation as k goes from 1 to 5 of 8 times the quantity negative 3/2 raised to the x minus 1. This is a geometric sequence, and so we will use the formula for the partial sum of a geometric sequence. That is, we're going to use S sub 5, because we're going to go to 5, equals a, the first term, and then 1 minus r to the power of n divided by 1 minus r. We have the ratio, it's negative 3/2. We have the first term also, which is 8. But let's go ahead and check. So we'll see if we do the first term is going to be 8 times negative 3/2 to the 1 minus 1, which would be 8 to the negative 3/2 to the 0, which would be 8. So it checks. Now let's use the formula. We would write this formula S sub 5 as 8 times 1 minus negative 3/2 to the 5ths divided by 1 minus negative 3/2. Let's continue. This will be 8 times, and then we'll have 1. Negative to an odd power keeps the negative, so minus negative will be plus. 3 to the 5th is 243. 2 to the 5th is 32, and we'll divide the bottom by 1 plus 3/2. Let's continue. This will be an excursion in arithmetic. So I'm going to come back over here for more space, and I will have, let's see, 8 times 1 plus 243 over 32. I need a common denominator of 32, and that will give me, let's see, 32 plus 243 would be 275 divided by 2, and the denominator would be 2 over 2 for 1 plus 3/2, so that'll be over 5/2. Let's continue. We'll have 8 times 275 over 32, and then we flip, let's find the reciprocal and multiply the 5/2, so we'll multiply by 2/5. Multiplying across the numerator, I get 4,400, and 32 times 5 is 160, and the sum reduces to 55/2, and if you want it in decimal form, that'll be 27.5. Roman numeral 3, infinite series. If the absolute value of r, the common ratio, is less than 1, then the infinite geometric series converges and has the sum S sub infinity equals a sub 1 divided by the quantity 1 minus r. If the absolute value of r, or the absolute value of the common ratio, is equal to or greater than 1, then we say that the series diverges. Determine whether the infinite geometric series is convergent or divergent. If it is convergent, then find its sum. An infinite geometric series is convergent if the common ratio's absolute value is strictly less than 1. The common ratio for the series 1 minus 1/2 plus 1/4 minus 1/8 turns out to be negative 1/2. In fact, you can check by multiplying an existing term by the common ratio and it'll give you the next one. So let's see what happens. The absolute value of the common ratio is the absolute value of negative 1/2, which is 1/2, and guess what? That's less than 1. So we can say that the geometric series represented for part A converges. Let's look at B. 1 plus 3/2 plus 3/2 squared plus 3/2 cubed. Now, we say that an infinite geometric series diverges if the common ratio is equal to or greater than 1. The common ratio for this geometric series is 3/2, which is greater than 1, so we say that this geometric series diverges. Express the following repeating decimal as a rational expression. There are several absolutely correct, acceptable ways to solve this. I'm going to choose to do this by addition. Let me show you what I'll do. For part A, we've got 0.2 and then 5/3 repeating. So just for visibility, I'll write that the S can be represented as 0.2, and I'm going to write 5/3 several times over just because it helps me to see it. Now, to begin this problem, I'm going to multiply that entire S through by a factor of 1,000. So 1,000 times S is, and when you do that, you move the decimal place over 3 spaces. So the numbers become 253.535353. And remember, the 5/3 goes on indefinitely. Now I will also multiply that term by 10. So I'll have 10 times S is equal to, and when I multiply by 10, the decimal moves to the right just one space. So I'll have 2.535353 ... Now I'm going to subtract. So 1000S minus 10S is 990S, and 253 minus 2 is 251, and we end up subtracting off everything that repeats. So 990 times S is equal to 251, and when you solve for the sum, you get 251 divided by 990. That is the rational form of the repeating decimal 0.253 repeating. Let's do this one more time for part B. That's 0. And then 9 repeating. I'll write S equals 0. Bunch of 9s, it repeats. I will multiply this through by 10. Then I'll get 9.9999 repeating. Let's just subtract the sum, which would be 0.999 repeating. When you perform the subtraction, 10 minus 1, gives us 9S. And then on the right-hand side, all of the 9s that come after the decimal, subtract off, so you get 9. Then you have 9S equals 9. And guess what? 0.9 repeating is 1.